Welcome everyone to this training session. I am so pumped up that you're here. Thank you for taking the time, community members showing up, learning about brazing. So this is something that, man, I sat in with Mike and Harold's training maybe about 6 months ago, maybe not even that long ago. And I was sitting through it and I was thinking back in 2004, the first time I did brazing in an HVAC program. And then 2005, 6, 7, 8, 9, doing thousands of brazing, like just doing tons of new construction, tons of renos. And I was sitting in this training session, and then Harold and Mike were going through it, and I'm just like looking at it. I'm like, I don't remember if I was doing this right. I know for sure I was doing some of it wrong. And over the years, especially when I first started out, nobody taught me. Was that older journeyman who was doing brazing for decades, but he was never taught the proper ways, but he did it right, and it did some of the good wells. But I seen so many leaks by me, and I seen so many leaks by other technicians just because we weren't taught the process. So I was sitting in this session and I was watching them go through this, and I'm like, I need to share this with my community. I need to share this with the people here because this is so important. Because I wish I had this when I was doing 1,000 joints a year, or 2,000 or 5,000, how many I've ever did over my career. And I'm super excited about this session. We're going to be diving into the foundations, what you need to know. We're going to be diving into how to properly braze. And you're probably doing this. I'd love to see you guys in the chat telling us how you braze, if you had leaks before. I know we've all had leaks in the past, but can we get better? Yes, we can. We're doing this live online, right? Or you might be watching the recording, but this is something you can go practice. Talk to your boss, talk to your service manager. You got pipe out there, go practice it. Practice it at home. Get better at this. This is a skill. And the better you get at it, you can save yourself time. You can save yourself money if you're a business. I am pumped up for this session. Mike, welcome to Refrigeration Mentor Podcast, and welcome to this training session. How you doing, my friend?
Doing real well, Trevor. Thank you very much. It is an absolute privilege for me to be here. I much appreciate you carving out this hour for me to talk to the folks out there. One thing I can promise your audience is that they will walk away from this and they will have picked up something valuable. That I promise you. So I think I much appreciate everybody's extremely valuable time. I know we're all busy people, so I'm going to move along if you're okay with that.
Let's do it. Let's smash it.
Okay, I'm with the Carpet Development Association. Thank you for having me again, Trevor. The Carpet Development Association, I just want to briefly say who we are and what we do. We're a not-for-profit association. We represent the global copper industry. We influence the use of copper and its alloys in the marketplace through education, hands-on, webinars, whatever it takes. We involve ourselves in standards, codes and standards, and we do tons of field support. So that's what we do. I'm the guy on the right. My name is Mike Belanger. I live in Massachusetts. My partner and my mentor, who's a near absolute expert in this industry, is Harold Moret. He's on the left. I don't know if Harold's on the call or not. I hope he is, but he's a superb talent. Just a couple of photos of what we do with copper out there. I just appreciate the artistic value of these photos and the craftsmanship that you folks contribute to the marketplace and the industry. Copper is used widely in a variety of applications: wire, cable, infrastructure, architectural, et cetera, for a lot of superior characteristics. That's not really the topic at hand, but I just wanted to mention that. And I can revisit any of these things if you folks choose to ask up follow-up questions. We're supported by major manufacturers, such as who you see right here. They're the ones who pay for me to be in front of you folks, like right now. Okay, this is a huge deliverable, everybody. This Carpet Tube Handbook that the Carpet Development Association, we publish, this is a free publication. You can download it at carpet.org. It's 95 pages of valuable information. How to join copper, characteristics, 25 pages of tables. It's a must-have book for anybody who involves themselves with copper tube, please.
And it's in the chat right now. If you want to download it here live, it'll be in the description. If you're watching this on YouTube later or listen to this on the podcast, so go to the description and download this one. And I know there's a revision coming out, so you'll see that as well coming down out here in the next couple months.
Outstanding. Okay, we also have on our website or in the copper tube handbook, you can access various videos. We have about a dozen of them that talk about the different ways to join copper, whether it be braze, solder, mechanical methods, flaring methods, whatever the case may be. They're all short and they get right to the point. So they might be worth a peek if you take a look. So I'm going to talk a little bit about soldering and brazing. They're very similar. And I'm also going to talk a little bit about purging. Okay, ASTM B828, that is the standard practice for making capillary joints by soldering. Proper training will eliminate joints that look like this. I've been in this, I started out as an apprentice plumber at age 20. I've done lots and lots and lots of soldering. I think I have been victimized by some weaker aspects of my soldering at times. These are little voids. And the goal here is to go over techniques so we have no voids. And you'll see what I mean. Some of these joints may never leak. However, to dramatically decrease or have zero defects, we're going to propose doing it the way ASTM prescribes.
Yeah, I've definitely done that. If you want to go back just for a second, Mike, I know for sure I've had water leaks because in a lot of walk-in boxes that I installed, we'd have to do copper pipe out from the drain lines would be copper going out. You trap it and then out. But I know for sure there was times when I either didn't clean it up well enough or there was something on it, like a sticker was right in that spot where I cut it, and I didn't get all the adhesive off, even though it looked like it was off, and then leaks down the road.
Okay. So we were all taught certain ways by our mentors. This is a quick video. I'm just going to hit real quick. It's a great short video.
Soldering a copper joint may seem straightforward, but there are a few hard-to-see mistakes that can result in weaker joints, causing leaks. Avoid these common pitfalls to ensure every joint is as strong as it can be. Once your tube has been measured, cut, and reamed, clean and apply flux to the tube and fitting. Then you can begin to preheat the tube and fitting. Avoid heating only one side of your tube and fitting. The solder will be drawn towards the heat and increase the chances of creating voids you can't see. This is true for joints in both horizontal and vertical orientations. To begin correctly, heat the tube before heating the fitting. This will ensure the tube expands first for consistent capillary space with the fitting. If only the fitting is heated, then the tube may not reach the melting temperature of the solder, resulting in trapped flux and voids that could lead to failures. The goal is to expand the tube inside of the cup while bringing both the tube and fitting up to the solder's melting temperature. Imagine the face of the joint as a clock face. Starting at 6 o'clock, slowly heat your tube until you reach 3 o'clock. Repeat this process starting at 6 o'clock and moving to 9 o'clock. It's not necessary to preheat the top of the tube and fitting during this step. Next, preheat the fitting. Following the same process as the tube, start at 6 o'clock, slowly heat your fitting until you reach 3 o'clock, then again from 6 o'clock to 9 o'clock. With your tube and fitting preheated, move your torch to the back of the cup. Start with your torch at 6 o'clock and push the solder straight into the joint at 5 o'clock. If it melts, then your tube and fitting have reached the necessary temperature. The solder will flow into the joint towards your heat source using a process called capillary action. Be careful though. If too much heat is applied, the flux may begin to boil away, resulting in a poorly sealed joint. While keeping your torch slightly ahead, move both the torch and solder around to 11 o'clock. Be careful to keep your torch slightly ahead of the solder. Failing to do so may result in voids being created. By the time you have reached 11 o'clock, the solder at the bottom of the joint should have solidified, providing a solid dam of solder. Then, go back to where you started, but now put your torch at 5 o'clock and solder at 6 o'clock, and repeat the process in the opposite direction until you've completed the joint by bringing the torch back to 11 o'clock. You may notice excess flux being pushed out of the top of the joint. This is normal, indicating that the joint cannot accept any more solder. Now the joint is complete. Let the joint cool naturally before using a dry rag to clean off any excess flux. For additional information and resources, please visit us at copper.org.
I know we're talking about solder right now, but I know for sure when I was doing brazing, I wetted so many joints. Like I've seen people just to try to speed up. Nobody told me, well, you shouldn't be putting water on there, and they may have. This was 20 years ago, but I remember when the first year or two, like just trying to rush through to cool them off. And because sometimes when you're doing a 2-in-1 or a three-in-1, these are big pipes. They take a long time to cool off, and you want to go to the next one, but you can't go until it's done to pull the insulation over. But I learned that from making mistakes and cracking afterwards. Does that happen when you wet joints?
Spot
Mike?
on, Trevor. Yep, spot on. Well said. So ASTM B828 6-step method. I'm going to go through it, and what I'm going to do for you folks out there is I'm going to provide the science. All of these points sound self-evident, and they are, and I'm sure you do it, but I'm going to give you the science behind each so you have a better recognition of how to attain zero defects.
I love that.
So needless to say, it's got to be measured, and the tube has to be fully inserted. It needs to be square cut. And I'm going to go over these points a little bit at the risk of being a little repetitive, but I'm going to, like I say, get into the science. This is important. No hacksaws to cut anything. Full insertion, very important. And I'm going to show you why.
And
Okay.
a big thing about that, Mike, before we dive in there, like just go back to that one with your tools. So it's important to buy the proper cutting tools. I've cut thousands of pieces of copper before, thicker ones, thinner ones, big ones, small ones. You'll have different sizes, but you can buy the blades and you got to replace the blades. And so they get dull. And I remember like trying to cut through pieces and squishing it really hard. And then if it's soft copper, bending it sometimes. If it's hard copper, we're making bigger ridges because I'm doing it harder. And so it seems like it made a little bit bigger and I couldn't fit it in sometimes. Then I have to get a file and file off the edges. Getting the proper tools is so important, and checking them to make sure that they're working properly.
That's a fact. And in fact, Trevor, the back of the tubing cutter here that does the reaming, they have wear points when they use time and time again, so you don't get the proper ream. And I'm going to get to the point as to why this is so important. Okay, so burr removal, inside, outside, very important. Okay, with the proper tooling, various ways to do it. Oxide removal, of course, with the
Or the Riemann one, though. I'm sorry, Mike. I want to jump back on this. The Riemann one. What happens when it's on a vertical and you're going downwards and you need to ream that? But it's already joined because this happens, right? And it's a. How do you prevent that copper from falling in there? Like, what do you recommend for the guys so it doesn't drop down? Because you're on the vertical now and you need to ream that pipe. Do you have any recommendation?
That's a good point. And like many things in our trade, there's a little bit of skill and experience level to that. In a perfect world, you might have thought ahead before you solidified that joint. However, retrofit, you're not always in that case. So maybe with the right tool, maybe like, a file might not be the case, but one of those little spiral reamers, something like that, and just being careful, right? That's all, that kind of.
I got to a point where I wasn't the vertical ones. I wouldn't ream. I would try my best, but it depended on the where I was at. I might not have reamed it out. And I know people say don't do that for one just the vertical joints. What are your thoughts? Should it be reamed on the vertical? Every joint should be reamed. What do you think, Mike?
Well, let's say, for example, you have to do 6, 7, 800 joints in an installation. I think if you take exception on that one joint, Trevor, I don't think it's going to be the end of the day, the end of the world.
Yeah. Everyone has their own opinion. That was what I thought, because I would rather not get the piece of copper in there to potentially get to the compressor and short it out, or plug up a TX valve.
Right. Yeah, you don't want shavings in there for the obvious reasons. In refrigeration systems, OEM applications with heat exchangers, medical gas in hospitals. So think ahead, gentlemen, like you always do. Okay, the oxide removal on the outside of the fitting, the inside of the fitting, the outside of the tube. We're going to get a little bit more into this. Fluxing, very thin film. We don't have to gooble it up too much, just a little thin film. Okay. And then the assembly and support is more important than you think. And I'm going to show you a visual as to why, particularly on heavy systems. When you want everything perfectly level, if you have a lot of weight on one side, you're going to get a little bit of a cocking, and that will affect the capillary space, which is where the alloy or the solder goes into. And I'm going to give you some outstanding visuals, so bear with me, folks. Okay. To Trevor's earlier point, don't quench the joint. That will cause contraction and cracking. Let it cool naturally. Clean it off. Clean off the excess flux. Okay. So I talked about measuring, cutting, reaming, cleaning, fluxing, assembly and support, heating and cooling. Okay, we're going to get into it a little bit more. Here's a good visual. Full insertion all the way into the full insertion into the fitting. Now bear with me because I'm going to show you the science coming up soon. Okay, the capillary space around the entire circumference of the tube, that's a critical space. These are manufactured products made for a reason. And so that's an important thing, and that can be stirred by some of these things that we're talking about. Okay, when you just saw the gray, that was the insertion of the alloy. That goes around the entire circumference of the tube inside of the fitting. This is why it's important. When you activate your system, the pressure that's activated, it's consistent throughout the whole joint, and that prevents any creeping or shearing or distortion. I think that's one of my favorite visuals in this entire PowerPoint. I'm going to move on. Okay, reaming. I think we all know the reasons as to why that's important. Okay, what happens is if you do not ream, you do create turbulence, which creates areas where erosion or corrosion can present itself. The outside, the deburring, very important. I want to go back to that slide. If you look at the top of the tube here, this is a side view. I'm showing here the flow and why you replace the burr on the inside, but the burr on the outside, if you look at the top, the very top or the very bottom of the tube, what happens is when you insert that, that pushes the flux back into the fitting, so it disturbs the ability to solder or braze, or solder in the case of flux being used. So the reaming is also very important. Fluxing, like I talked about earlier, just a minimal amount all the way around the tube, inside the tube of the fitting. And that wets the surfaces and protects against oxidation so that you can get a proper solder joint. Okay. That little thing there called interstices, it's a funky word. Bear with me. I'm going to talk a little bit about the science of that. Okay, so fluxing is important. Remove the excess flux. Okay, it is a little acidic, so we move it with a clean rag, not a dirty rag, not the rag you use to change the oil in the vehicle. Okay, so overfluxing can cause some corrosion in the inside. It disturbs the patina, which is a natural protective layer. So overfluxing, not good. Okay, just real quick to go back, if you think about the video I showed you folks earlier, we're preheating the tube, then we do the fitting, then we apply the alloy, and then we clean it off. Okay, that was just real quick visuals. Okay, how do you solder? Let's go through this. So we talked about the different methods, and we're going to talk about them a little bit more. Okay, preheating of the tube and fitting. The procedures here are really important, okay? I don't profess to be the best brazer on this call here, folks, but what I have been is I've had the luxury of being trained properly on these techniques, and that's what I'm going to show you. Okay, so we preheat the tube first, starting at the bottom, as you recall from the video, and we work our way up on one side, and then we work our way up to the other side. The heat rises, so you don't have to worry about the top. Then we do the fitting. Okay, everybody with me? Okay, pretty good visuals. Okay, we don't have to do the top. We talked about that. The heat will rise. We'll be okay there. It's important to preheat the tube first, because what happens is if you do the fitting, see the expansion? See how the capillary space, that would be this area right in here. It's been distorted, okay? Yep. Not the end of the world, but we want to do things right. Like my father said, if you're going to do it right the first time, because you may not have time to fix it after the fact.
Yeah, I love that. So I got a question for you. So basically, you want to heat the pipe, the third, a third, and a third first. Then you move on to the joint. Then you heat that a third, a third, a third, and then you apply your alloy. Is that correct?
Yes, yes. And we're going to go through that in some really cool visuals. Okay. Okay, see how the tube expanded? So the capillary space is being maintained as it is supposed to. Okay, this is a good visual here because what we talked about in the video, the alloy or the solder always follows the heat. Okay, so here's what happens here. It only went in halfway because it follows the heat. All right, so you didn't fully insert the alloy or the solder in that entire capillary space. That's a danger point. With the proper application of heat, you get full insertion. Everybody see that? Everybody good with that? The application of heat's really important. The alloy, the solder always follows the heat. So in this case, we really weren't using proper technique. We had the alloy very far away from the heat, and therefore we have a area of concern right here with the void.
Okay, so those that are listening on the podcast later, basically what Mike's shown is the pipe is inserted, but they're heating up the coupling first, and then they're adding the alloy to the opposite side of the pipe, where you want to follow the heat, right, Mike? So you have the heat,
Yes.
and then as the heat's going to the say the right before that by your whatever is 1 centimeter, 2 centimeters before, but you're following the heat afterwards, right? So you have the heat going, and then you have the filler following it. Is that correct?
Perfect. Perfect. And in this case, we're not doing that. If you remember the slide I showed 2 or 3 slides
Yeah.
earlier, that oil was following the heat. Okay. This is just a side view, same exact thing.
Yeah.
See how the void is created, folks out there in cyberspace? Okay.
Yeah. I've done that before, Mike. Just
We all
for
have.
sure.
We all have. Capillary action. Okay. We've talked about that a little bit. It's a terminology I became more familiar with once I came to work for CDA, despite all those hours and all those joints I did previously, right? Okay. It's the ability of the liquid, the alloy, whatever, to flow in a narrow space. Okay. And I'm going to show you a visual of that. Okay. This is something we do when we do the hands-on presentations and we're showing instructors on certain things. Capillary action. We take a couple sheets of glass. We dip them in a little panel water that's red, you know, just food coloring, that kind of a thing. There's 2 panes of glass. We put a toothpick in between them. We clip them top at the top with a binder, and it just naturally flows upward, defying gravity. That's called capillary action, and that's part of the process when we apply these techniques to joining copper via solder or braze.
Yeah, I think that's so important because I think that's where a lot of things were missed. Even me, right? I've had a lot of leaks in it, and you look at it even with a mirror, right? Because you can't get to a lot of the spots, especially in refrigeration. There's so many tight spots, so you got a mirror. Oh, it looks pretty good, you know, and then all of a sudden you have a leak there. So you know, and it happens. But with these practices, you know, it can fill that stuff up and not have those voids.
Right. Okay. Once again, I'm going back to this slide to show you something here. Of course, looking at it front to back, that would be the tube, of course, again, and the fitting is the outside circle. So we're applying heat, and now we're going to apply the alloy. Okay. Watch what happens. Alloy or solder following the heat. Great, great visual. Okay. Watch now. Now we go to the other side. See that?
So this is what I didn't do, Mike, for sure. You know, I probably did it, but it wasn't someone taught me that. I would just go rip right around, where that's not what you want to do. You want to do half the.
You might be being a little hard on yourself, Trevor.
Well,
Okay, folks.
I
So
love it.
we're not done yet. We still have work to do here. Okay. See how we did that? Now we still got to get that top. What I have learned factually is that's where most leaks occur. Okay.
Yeah.
It's really important to fill that up, completely fill it. And as you may recall from the video, if a little comes out at the top, don't worry about it. You filled the void. You did your job. Okay.
Okay. So
Now,
okay. So I think let's just go back. I want to. So when you start, you heat up that first pipe that's in the tube or the fitting. So you heat that one up first, then you heat up the fitting itself. Then you start and you have your heat running around half the thing and you follow it. So it's like in the visual, Mike has the torch going, fills up kind of like a third of a half or quarter, I guess, and then fills up the other quarter as that alloy is following the heat. Then he goes to the opposite side and does the same thing, comes right back around from that thing and fills up to that point, right to the point where there's just a little gap left. Then he moves the heat to the opposite side again and then fills that gap. So that's the steps on doing it. And I used to go all the way around. Everyone who's listening, I used to just go all the way around. And sometimes if it was a big joint, I would have to go to the other side because I'm on a scissor lifter. But it wasn't something that I was trained to do. I just did it because out of necessity. So great job, Mike.
And we're talking a lot about technique here, Trevor, but we're also going to get into the application of heat, which is a critical component, needless to say. We're going to get to that, okay?
I love it.
The reason I like this picture is because two things, the right hand and the left hand. The left hand, look at where the heat is, okay? It's at the back of the fitting, and the heat is being dispersed from the back of the fitting onto the tube. Perfect application. Great concentration on the top of the joint where most failures are. Now, folks out there in cyberspace, look at the right hand. See the alloy? I'm not painting it. I'm not brushing it on. I'm pushing it in. It's following the heat. That picture is fantastic for demonstration purposes on the top of that joint and the application of heat.
Yeah, because if you do have like a gap in there, because I've seen this before, like I'm just going to put a shoulder on it. You don't need to put a shoulder on it, because even if you put a shoulder on there and there's a gap, you're still going to get the leak. That shoulder that you put on there is not going to stop if you have no filler inside the fitting and the pipe. I know from experience. So
that shoulder is more has to do with the strength of the joint in terms of vibration, expansion, contraction. I'll talk about that briefly as we progress here.
Do not quick quench the brace joint.
I had to include that slide because that's my partner, Harold, and he's got a great voice for radio. Do not quick quench the joint. Keep the water off of it, like Trevor spoke about earlier. Okay. Do you folks remember earlier I talked about interstices? If you look at this little visual, this is the inside wall of the copper tube. Excuse me, the outside wall of the copper tube or the inside wall of the copper fitting. You can't see that with the naked eye, but there's these little things called interstices where the solder or the flux will embed themselves in that once applied to eliminate shearing or creep, okay? And this is a microscopic view of what the copper actually looks like. We can't see that with our eyes. And those interstices, now you see the filler metal in the middle there, folks, okay? With the proper application, see how it's embedding itself in the interstices, that complicated word interstices? That helps create a rock solid joint, okay? Good. Brazing.
I love this.
I do too. 6-step method, exactly the same pretty much as soldering, but obviously the biggest difference is the heat required. We're going to talk a little bit about that. Thanks for staying with me, everybody. Okay, so we have some frequently asked questions, and I'm going to go through these things because these are important. What type of alloys are normally used? Plumbing and HVACR applications. When must brazing flux be used or not? What is the minimum depth of penetration necessary to obtain a satisfactory braze joint? Why must the anneal pressure rating of the tube be used if a joint is brazed? These are important points. We're going to get through each of them briefly. Okay, brazing alloys regulated by AWS, American Weld Society A5.8. I guess the big deliverable here is when you're in the field or working on an installation or whatever your responsibility is, specifications are important. Manufacturer's instructions are important. You can't just use what's on the back of the truck and it's convenient to grab it. It may work. It may have worked 100 times, but being the skilled craftsmen that we are, we like to do things right. We like to pay attention to manufacturer's instructions. For most of my life, I made the mistake time and time again of not reading the manufacturer's instructions, and I paid the price for it many, many times.
Yeah, me too. One of the big things is this is what I learned from you and Harold when I was in that first training with you guys, was that I always use 15% silver because that's what I was told that I need to use all the time. And then when I talked with you and Harold about it, that you're like, that's just the spec. So that just remember, what is the spec of that job site? That's what you use, because 15% solid, 6% could probably, and that's what I asked Harold, could I use 6%? He said yes. But if you don't look at the spec, what that customer specs or what that engineering spec, even though 6 will work, you have to go with that, because then you're liable for that stuff. So that's why Mike says don't just go pull stuff out of your truck. Usually your company's supplying this on an installation job, but I just wanted to point that out because I always thought, well, you need 15 because it's stronger. Well, no, 6% is strong too, or 8%, whatever is out there. Do you want to talk a little bit just on that, Mike? How is important? Why is it so important when it's spec'd by a customer to use the right stuff?
It's a great point. Um, First of all, silver is extremely expensive. So if you don't need to use like 50% like Trevor talked to, and you can use a lesser amount, a lesser quantity, it's more economical, number one. But number two, the reason these alloys are specified or required are for various reasons. It's different chemical compositions of what you're brazing, different melting temperatures, the different base metal compatibilities. There's reasons as to why each are specified. Okay. And, refrigeration, OEM, medical gas, whatever the case may be. So pay attention to the written word.
Yeah. Well, we're great in the chat. I'm looking in the chat. Somebody says, Jay says, train specifically does not allow 7% at all. They specify 15%. So this is coming from the manufacturer. Could 7% work? Probably. I don't know, but it doesn't even matter. You go with what that manufacturer says.
I applaud the gentleman who piped in and said that, because he's paying attention and obviously a skilled leader. Okay. Brazing alloys, two types. The B cup is most often used for HVACR medical gas, and it's when you're brazing copper to copper. Okay. And the tube, the fitting, the alloy all have phosphorus. Therefore, you don't need a flux, and you would use the B cup alloy.
And Mike, I just want to jump in. Like Harold threw something in there. We were talking about soldering applications at that point, right? So just remember, everything we were just talking about was about soldering. No need to cap the solder joint. We're going to get into it. You do need to cap a braze joint. Okay.
Yes. Okay. The other type of alloy is when you are joining dissimilar metals. Okay. And that would be bag, that B for braze, AG for silver, has a higher content of silver in the alloy than the B cup. And you would use that when you're doing dissimilar metals. So for example, if you're brazing copper to steel, copper to stainless steel, copper to aluminum, you'd be using a bag alloy. Okay. Oftentimes, Trevor, the question will come up, what about brazing copper to brass or bronze? Okay. Those are dissimilar. You would use a bag unless you were using a suitable flux for B cup. Okay. Yeah. I don't mean to complicate things for the audience. Just pay attention to the application at hand and the instructions.
Well, in refrigeration, there is tons of brass valves you got to braze in, as well as silver, stainless steel. I apologize. That has to be brazed in or welded in, depending on the manufacturer. A lot of the times, they'll put like a copper coating in them as well, depending on the manufacturers to that. So you got to understand the components that you're brazing in. Is it dissimilar or not? You got to check that out.
Excellent. A little bit more on B cup and bag alloys. Tube, if you look at this triangle, it's just a visual. Tube, fitting, filler metal, they all have phosphorus. Okay, in which case you phosphorus, phosphorus, P for phosphorus. So no flux is required. Everybody with me? Okay. And phosphorus, it just, without getting into real too technical scientific detail, it acts exactly like a flux. Okay. If you hit the tube is has phosphorus, the brass fitting does not have phosphorus, then the filler metal, you would use a bag alloy. Okay? Brazing flux required.
And because that doesn't have the phosphorus, is that correct? That's the science behind it?
Perfect. Perfect. Phosphorus is the key word. Okay? Brazing fluxes prescribed by 85.31 American Weld Society. Different fluxes for different applications. I'm not promoting any manufacturer, but different fluxes for different applications, similar to the alloys. Just pay attention to the specifications or the manufacturer's instructions. That's all we ask. And you can get away with various things, ingredients for various applications. However, some are pretty more specific than others, so we need to pay attention to those kind of things. I think this is a good visual, Trevor, because when we're in the field, particularly in the earlier parts of our careers, and we're applying heat and things like that, it's all trial and error. We don't know. So this is a pretty good visual for all of us. Room temperature 72 degrees. I think the room where I'm in Massachusetts right now, it's probably more like 76, but that's okay. Water boils at 210, everybody, as we know. Okay, flux. Flux bubbles somewhere between 600 and 800 degrees. Okay, we're applying the heat. Visualize yourself applying the heat. Okay, and the temperature's rising. Flux starts to become clear at 1,000 degrees. And now the alloy, the brazing alloy, typically melts between 1,100 and 1,550. That's when you get the flow into the joint, the capillary action. Melting temperature of copper, 1981, 1,981 degrees. So just gives you an idea. Early in my career, yep.
I've definitely seen people put holes in pipes before, like working tons of renos late at night, working 15, 18 hours a day, 7 days a week. And I'm just using oxyacetylene because I've used acetylene torches, which are really loud. That's what I started out with. And then I learned about this something called oxyacetylene. Maybe we'll get into it a little bit, which is way hotter, which is way more impactful. Like I love that afterwards. For 2 years, I was using turbo torch and it was so loud. I didn't even know that you could get a flame that's so quiet as an oxyacetylene. Do you want to talk about that? Will we get into that? I can't remember if we're going to get into the two different types of flame methods.
Let me think. Am I going to get into that a little bit?
No, I don't think we are. I'm looking at the slides now. But what can you talk a little bit about the differences? When I was looking at that picture that you were doing, that was an oxyacetylene setup. Is that correct? In the picture you
Yes,
were
it was. Yes, it was. Okay.
Did you, in your career, were you using more just oxygen torch or turbo torch? We call it, that's the brand name, I think, but acetylene versus oxyacetylene. That's my question.
It depends on what they're set up for. A lot of times when I go into the apprentice halls, they seem to be set up with the oxygen acetylene, but
Yeah.
more often a B tank, just a
Yeah.
standard 40 cubic foot B tank is perfectly fine. And I think what's important there is the two things to remember about that, and they're more transportable too, right, for the mechanics. I think the important thing to remember about that is the duration of, like, say, for example, a 40 cubic foot tank will last for. And then you have the torch handle, but also the right size tip, Trevor. Okay.
Yeah.
Different tips for different sizes, like the sizes can range from, like, say, anywhere from 8.3 to 8.32, 8.32 being for larger diameter versus 8.3 for the smaller diameter.
Yeah, I know. I remember when I first started out, I had one torch tip or two torch tips.
Yeah.
And then I was trying to do like a 2-in-1 with like a 7 or something. And I was like, it takes forever. You know what I mean? Then I got a 32 tip for all the big pipe, and it was like a tenth of the time to do the joint. And it's done right because you can't heat it up fast enough with a small tip. You can't heat up a big piece of pipe with a small enough tip. So that's something I learned.
Right. Yeah. Well, frankly speaking, most of us use tools that were given to us by our employer or our mentors or our fathers or our grandfathers. So one of the things behind this classroom is now we think beyond that and using better methods and better tooling.
Yeah.
Minimum depth of penetration necessary to attain a satisfactory braze joint. Very important. There's this thing called the 3T rule, not CDA's terminology, AWS, American Weld Society. And what that means is, I'll give you a better visual. Whatever you see, the tube is 1/4 of an inch thick. That would be the tube on the top, the visual. The one on the bottom is 1/16. Excuse me, that would be the tube, the thickness, 1/16 thick tube. That's the tube. The fitting is 1/4 of an inch. Bear with my mistake. Okay, 3 times the lesser wall thickness is the depth of penetration required to attain a satisfactory joint. Okay, so if you look at 1/16, that's the lesser of the two.
Yep.
3 times that is 3/16. That's your proper depth.
Okay. So you don't have to have a full all the way at the end of the day for
No.
for like this example here.
For this application, you are correct. There are times in specifications that call for full penetration or 81% penetration. Not here, okay? Not in the refrigeration business, unless prescribed by the owner or the client. Okay. The fillet is important in brazing, and I'm going to give you some science as to why. That would be around all the circumference. Don't forget, we're looking at a cross section here, folks. You all know that. You're mechanics. Okay. With vibration, expansion, contraction, things in the equipment that you folks install, the critical applications, that can result in cracking. Okay. So therefore, we like a well-developed fillet. Okay.
And when you say Philip, that means shoulder.
Yes.
Okay, so just remember when we talked about a shoulder earlier in the solder, you think about plumbing. So if you're doing a walk-in box, again, you're soldering the copper pipe that's on the drain line. Now we're talking about the refrigeration pipe when you're brazing. So brazing these ones here, you do your fill, but now your fillet, which is actually a shoulder around, so that reduces cracking. Is that correct? Leaks due
Yes.
to cracking. Great.
Yeah, and brazing is specified because it's they want a more secure joint than a solder joint. It's a stronger joint. So to your point earlier, Trevor, as long as you get the full capillary action going on in a solder joint, you don't necessarily have to cap it. I know you feel good when you do, but with brazing, it's more important because there's more stuff going on that's critical.
Yeah.
All I wanted to show you folks here, I have not brazed all my life. I've done a lot of soldering. Brazing was new to me, but I learned from one of the best, Harold Moret. And the first time I took the braze test for the ASSE 6010 certification, I passed it with flying colors. This was requiring full penetration, and they measure it, both sides. And they also look for deburring, reaming, and fillet.
Okay, let's go through that again. So if because you're gonna get this test, it doesn't matter where you're at in the world, you should be testing yourself anyway, and not be scared to be like someone challenges you on your joint. They say, "I want to cut that joint out and look at it." You should be proud. Yeah, this is awesome. Cut it out. Take a look at it. Here, I'll cut it out for you, and I'll show you how good that weld is. So step one is to do the proper heating. You heat the tube, then you heat the fitting, then you follow the heat with your filler. Your filler should be either, depending on the size, I would say just fill the whole thing, but you just said it could be 80% if you wanted, depending on the size of the tube and the fitting. So now when you're doing a copper test, and this is a test that you had to do, you had to pass this test to be able to braze. And we do that here in Canada as well. You got to pass your brazing test. They cut it open. They do this. You need to see that filler right along the middle there. Let me just pull out my thing. So right along here, you need to see this. And then along here, you need to see this. Is this correct?
Where I'm looking, just at the very top, they were looking for the fillet. See the fillet?
The fillet right here.
Yeah.
Okay. So they're looking for that. So that's one point of the test. Are they looking for this right here in the test?
What do you
right around the middle? They're looking
definitely. And you know what? So what happens is if you look at the one you're looking at right now, Trevor, the bottom, the full penetration is perfectly evident because of the angle of the photo, the phone. Couldn't really see it on the top. However, all they do is they take that little finger knife and they scrape off whatever little residue, and it's very visible. And the people who either pass you or fail you, they're not that lenient, if I may say. You know what I mean? You gotta have it. Yeah. Good. One point I'd like to point out to your audience, please, is all this takes to do it perfect. I don't know, perfect is the right word, but proficiently is practice. Not a lot of practice, a little bit of practice, but practice doing what we're talking about. Let me give you an example. In New Jersey, a couple months ago, I did classes for 60 third-year apprentices. These apprentices were excellent. I was so proud to be affiliated with them, and I gave them great training. And then we went into the shop and we did this for every single one of those students. And most of them didn't fail. And it wasn't because they weren't talented. It was because they hadn't practiced. They know how to take what they learned, and now they got to practice. And I promise you, you do 4 or 5.5 inch joints, you got it done. It's like riding a bicycle.
Yeah. I got a couple of questions. How do I know if the the brazing is correct? They said soldering, but this is brazing. How do I know if the brazing is correct? You got to cut it out. You got to cut it out to check, right?
Yeah, so what they all have various stationary portaband saws that give you a nice square cut, nice safe cut, wear your safety glasses, et cetera, et cetera. But this is a pretty common way of doing it. And, when I was practicing after Harold taught me, I would use my Sawzall. And of course, I didn't get a square cut, so I was embarrassed to show anybody. But this was done professionally.
Yeah. And you can see how this was nitrogen purged. There's no carbon in there.
We're going to talk about that next.
I think. Yeah.
I think we're good for time, so I'm going to keep going here, okay?
Yeah, let's do it.
Okay. This is important in annealing. I'm going to go through it quick, but in annealing, when you apply that heat to braze, the physical characteristics of the tube is altered. It's actually softened.
The annealing temperature of copper is approximately 700 to 1400 degrees Fahrenheit. And most brazing alloys have a melting temperature above 1150 degrees Fahrenheit, well above the annealing temperature of copper.
Why that's important, you see where I've yellowed softens the tube. The joint is still powerfully strong, but the maximum working pressure of the joint, because the tube has been softened, has been lessened almost in half in the case of 1-inch type L. Okay, all this information, folks, it's all in that free documentation that we give you in the Copper Tube Handbook. Magnificent go-to book. Please take a good look at it and pick out the things that are important to you.
You do have to remember, though, and you might get into this. Yeah, maybe you're getting into it right here. That's okay. Let's get into anneal, because this is important. Annealing versus drawn copper, because I've had this conversation in my CO2 design courses and in other courses about, well, what happens if I anneal it? This is something you need to go back to, especially the copper manufacturer themselves as well, because some of them, most of them for sure, Mueller. I had a conversation with Chris Mueller. He's been doing it for decades all around North America, and he's like, their copper, especially their high pressure copper, is using their annealed ratings when they're publishing their thing. But what Mike's showing you here, though, is when you do annealed, it derates it. And then you'll look at some certain size pipes will have, and I think we might get into it. They by ANI or ANSI standard, they will regulate, even though it says 500 psi, they'll do a 700 psi rating. And can you talk to any about that? I know we talked about this a little bit before, and I can pull up the documents that show it. But there's certain size pipes where they'll say that's 700 psi rated. Do you remember us talking about that, Mike?
Well, when you say 700 psi, you're talking about a joint rating?
Yeah, annealing. The pipe being.
Okay. Yeah. You know what, Trevor? I prefer to defer.
Yeah, that's okay.
Copper Tube Handbook. You know what I mean? So, like for example, with a copper press system on refrigeration where the tube is not annealed, that 700 psi. Okay, but limited on the application in terms of temperature, vibration, those kind of things. So I prefer to use the Copper Tube Handbook as the manual that I would prescribe. You're talking even with annealed 1-inch type L, 500 psi. However, it is dropped down from drawn at 850.
Yeah,
okay.
So you got to understand that,
strong joint,
especially when you get into larger applications and newer applications like CO2 refrigeration, right? Where we have to use higher pressure copper, because the standard that you'll see out there are yeah. So UL approves it. This is it. So right now, copper tubes, streamline ACR type L hard lengths and ACR K hard lengths up to 1 and 3 for L and 2 and 5/8. And I think you got a slide on this. UL approves for 700 PSI. So this here, the UL's approving, but this is not the copper handbook. And I've had conversation. Well, the copper handbook says this, UL says this. So this is something we might be able to take offline, but I want everyone to understand that. Go into the manufacturer's document. They're going to state this in the document to make sure that you're using the right piping for that job. Okay. And then fittings on top of that are different.
We are going to talk about that slide. You're right. We're going to get to that.
Yep. Love it. Okay.
Thanks for bringing that up. I'm going to go through purging because it's really important. And frankly, we run into many instances where we get called purging hasn't been done properly. So I'm going to go through it real quick. Okay. Very important. If you look at the fitting on the right without the inert gas purge, that's the oxidation. That is not good. That residue is not good. Okay. So again, the photo on the right, if you look at the bottom tube, nice job with the purge. The top tube, there's no way you can tell if that's been purged properly or not. It's just physically impossible. It has to be done with an oxygen analyzer. I'll show you what that is. Okay, so typically we use nitrogen to purge. And what happens is you hook the tank up to the tubing, and right now there's all air in it naturally, right? So before you start the purge, the Braze process, we have to apply the nitrogen, the purge gas into the tube, and we have to get it all out, the air out, all out 100%. So this is just showing you what's happening. As the nitrogen goes in, we still have oxygen in the line, and we have to make sure all the oxygen is out. The blue represents the nitrogen. Okay, now we're good to go. Now we can purge. Braze. Okay, the oxygen analyzer, that will show you that there's 0%. That would be on the one end of the module or the tubing, and that would show you that there's no oxygen in the line. So you braze and you continue to braze and let the nitrogen continue to roll through right through the cooling process.
That's so important. Like, this is something that I've even had conversations with technicians coming through our supermarket academy. Like, I'm working with some old guys. They've been doing it for 20 years. They say, I don't need a purge. They don't purge, and there's not a problem with that. There's a major problem with that. When you have systems with mineral oil, it wasn't as big of a deal. The mineral oil R22 system wasn't peeling all that copper oxide off, even though they were supposed to do it 20, 30 years ago as well. But nobody just did it because they never seen the issues. Now, you go to a retrofit and you go to from R22 system to 448, 449, for whatever the refrigerant is, and that's POE oil. It's going to start to strip all that carbon off there, and it's going to take it and fill in your filter dryers, your TX valves. This is why you need to purge every single time, every single joint. Maybe if it's the last joint, you know what I mean, and you cannot be purging at that time. Okay, one joint out of the whole thing, but every joint needs to. And I've seen people have to cut out tons of pipe because it was spec'd to be nitrogen purged, and it wasn't, and they had to cut out, and it cost the business a lot of money because it wasn't done.
Very important. Okay, for the sake of time, I'm going to move on rather quickly. We only got a couple more topics. Dissimilar metals, copper to black steel. We talked about this a little bit earlier. You need to make sure that you use the right alloy. In this case, dissimilar metal, it would be a bag. Use the right flux. Same with stainless. Make sure, again, dissimilar metal, you'd be using a bag alloy. Make sure you use the right alloy, the right flux. Okay, fluxes, same thing. Okay. In our tube handbook, it talks about all the various B cups. And alloys, bags, and the different contents of silver, phosphorus, zinc, etc., with the temperatures, melt temperatures. So it gives you an idea of the various alloys available for the various applications.
Mike, do you want to go? Yeah. Do you want to go back to the slide where it's dissimilar metals, just to show people how it's important? So, like right here, this is where I think a lot, even me, I struggled with brazing dissimilar metals for a while because I put too much flux. I not put enough flux. I didn't sand it enough because a lot of times I was doing retrofits. And so when you're taking off like 20-year-old insulation off of a pipe, it's all green or black, and then you got to clean it really well. But I think I've overheated flux before, and I think that could be an issue. Want to talk a little bit about overheating flux? If I overheat it, is it going to make it sink in properly, or how? Because that, I think that was a big issue for me. Look how beautiful this is right now. If everyone's looking, it's in a vise. You got a fitting on there. You got the tube in there. You're brazing down. That's not what it is in the field, guys. You got a 90 and it's on the top, and you got to try to hold that pipe in there because it's a little bit off and it's sliding down, and you got no one there to hold it for you. And you got to try to do an up braze, and it's dissimilar metals. Do you want to give some tips on that? Because I think this one here is, I've had a lot of fights with dissimilar metals in my career.
Yeah. Okay. So I think originally you were asking about the flux aspect of the joint.
That's
Okay.
the first question.
So if you remember the visual I showed a little earlier of the thermometer with the different things happening, you can burn or melt the flux. Okay. And so when you're brazing a joint, a lot of it is visual, and at about 1,000 degrees is the actual when the flux is able to be an influential ingredient in the process. Okay, because the alloy is going to melt shortly thereafter. So if you're brazing, you want to make sure you achieve what they call that liquidus state. When the braze alloy actually becomes liquidus as opposed to solidus, which is like when it starts to melt. Okay, it starts to melt, and it's gonna, you're applying it, and it looks like it's beading, and it's not really going in with the capillary action. You want to achieve that liquidus state. So it's a matter of the application of the heat. I don't know if I answered your question properly.
Yeah, no, that makes sense.
And
Right.
in flux, there's various fluxes, and the only reason I show it is because various fluxes have various temperature ratings also, and compatibilities with the different bare metal compatibilities. Okay, so
Yeah.
you need to kind of pay attention to that stuff.
I
Okay,
love that.
no corrode flux like my grandfather gave me like 50 years ago, and I'm still using it. That's not what you want to do on a brazed joint. I'm saying that comically, just so people will get the point. Okay. The only reason I put this up there, folks, is you see the different classifications for solders, alloys, etc., based on the different applications. That's the only reason. Just as a reminder, a tickler. Same with the fluxes. Okay. We're going to talk a little bit about the higher pressure refrigeration applications. Trevor referenced that earlier. We use to 700 psi. I think this is what Trevor was referring to. That's using ASTM 280 tube, 16.22 fittings, 700 psi. I got a better visual that sums this all up.
And the thing, I'm just looking it up now, trying to sort out what I was talking. So they say for hard length, for an example, the K copper can go up to 2 5/8 and is approved to 700 psi. So now my question is, so when I'm doing that joint, does that you're just doing a joint, you're not annealing the pipe and bending the pipe or anything? Because that's when I think of annealing, I'm thinking of I heat the pipe up and I'm bending it to a 90. Would that derate that specific section, that 1-inch section, when you do that?
I'm going to go to a slide to answer that question if you don't mind. Okay.
That's perfect.
So this, can everybody see this full slide? Can you see that last column on the right?
Yeah.
So these are the various, if you look at the, if you can follow my cursor.
I love this slide.
This is a publication by a manufacturer, okay? And at 1885 PSI, they have a tube. It has copper iron in it, and the fittings have a copper iron in it. And when it's brazed, that can be rated to 1885 PSI. That's a transcritical system right there.
Yeah.
If you go to a lesser requirement for PSI, Trevor, same fittings, the XHP fittings, which have copper iron, but now you use a tube which is thicker than type K. It's called an HP90, manufactured by this particular manufacturer. They'll give you a 1305 PSI. Where you were talking earlier, and you mentioned this manufacturer, okay, standard ACR fittings, type K, 700 PSI, up to 2.5/8.
And when I talked to Chris about this, he said that's their pipe, annealed or not. So up to that, they said annealed not. So you always want to follow up with the manufacturer and talk with them, if you're unsure, because I'm continuing to learn this stuff as we go. You want to know and you want to learn yourself and read it from those documentation. This is a documentation here that I've got from Chris. I use this in my CO2 course. You want to understand this. You cannot put the wrong pipe, especially in a CO2 system. You cannot take K copper and put it on a high side, or L copper and put it on the high side of a CO2 transcritical system, because you're going to run into issues because the pipe is not rated for those high pressures. I've seen it. So this is a great slide. I love that, Mike, that you showed that one. And there's this is one manufacturer, like you said, Mike. There's K65 is another one if you're around the world. So it doesn't matter the manufacturer to me. You got to go to that manufacturer and double check what their spec is.
Definitely. And to those higher pressures, those transcritical systems, you have to use the XHP fitting, which has the copper iron, in order to achieve this. When you go down to the 700 PSI, K or L, standard fittings.
Yeah, that's a big one too. I've seen that as well, like the wrong fittings using with the pipe. So these are some things you need to look at.
Don't want to take up anybody's valuable time more than I already have, Trevor.
Dude, we crushed that. I love it. We got a bunch of questions here that I want to get through, and I want to talk about it. But at first, I want to thank you so much, Mike, for going through this. I know we smashed this one out. Hopefully, everyone took a few things away. One of the questions that I've seen, and we answered this, why do we have to add the shoulder on brazing? Do you want to just answer that right quick? I know we answered it.
Yeah, when you're talking about refrigeration systems in particular, maybe around heat exchangers, original equipment, you are going to get vibration and expansion contraction. And because of those challenges, that's one of the reasons why they go to a Braze system. So therefore, that added security is achieved by filling that fillet. It strengthens that circumference around the tube. And it is important.
Yeah. And when I worked at Copeland, I had this contract years and years and years ago. They would do something like tandem set compressors. So they'd have a T holding the two compressors and a discharge would go out. And so when one compressor would fail, we would always unsweat stuff. Compressor manufacturer wants you to cut it out. You know what I mean? Basically, cut it out and replace it that way. Don't unbraze. But what was happening? They would unsweat the compressor at the T, right? So they'll pull it out. They put a new one in, braze it back, new one, and all of a sudden, like after a month or two, that T would crack. And they were like, "You guys are selling terrible teas." But what was the problem there, Mike? They were heating it up multiple times, right? Cooling it down, heating it up, cooling it down, heating it up, and the joint would crack. And then after they replace it with they either cut it out or they replaced that T, they never ran into that problem again. So just remember, if you do multiple anneals to copper tubing or fittings, it could cause it to fail.
Yeah. Forgive me for spacing out there for a second. I get distracted. However, the other thing too is you only want to braze a joint once. There's no going back to the well.
Oh, there you go.
Yeah.
So and I've done that lots of times, unsweat something, push it, put it back in. So now that's another good point. How many of you done that? That's still in the call. Put a thumbs up, or have you ever done that? You unsweat it and then use that same fitting again. I've definitely done it, and you're not supposed to.
You're more likely to get away with it with soldering, but not brazing. The chemical properties have been disturbed at that point. Yep.
Oh man, that's huge. That is huge because I know I've done that for sure. Here's another one from a good friend Tom. So tips to learn, like how to analyze your joint. So we've talked about analyzing you got to cut it open and look at it. I'm using engulfed heat. I probably don't pronounce that right. Or too much. So flow from the manufactured torch welding is not really working for brazing, or have I been doing it wrong all the time? Well, you got to follow Always got to follow the heat, but engulfed heat. I don't know what that means. So Tom, if you are still on there, elaborate a little bit on that heat.
Was he asking on how to analyze the joint?
He did ask that, how to analyze his joint. Yeah.
Well, the only thing
He
I
meant
could
enough,
offer,
enough heat. Okay. I'm using how do I analyze joint if I'm using enough heat? Oh yeah, great job. Thank you. Thank you, Tom. Yeah, that's it. How does he analyze it?
I guess if I understand his question properly, visually, if that's what he's talking, if what
Yeah.
Tom's referring to, it would be the flow, the capillary action, the free flow of the alloy into the full insertion of the joint. Okay, that's a visual. All
Yeah.
right. If
Okay.
he's talking post installation test, they have these obviously there's a standing pressure test, etc. But they also have, in a real complicated situation and sometimes necessary for tie-ins and things like that, these things called ultrasonic devices, Trevor. I don't know if that's what Tom's going with that, where
Yeah, no, I think what you said there is that because most of the people, you're not going to be cutting this out to take a look at it, right? You want to see, but it's that
right.
visual inspection, do it the proper way. So you're following the heat on one way and then you go back to the other side on it, but you're pushing it in. So you're watching it suck it in and not
Oh
drip
yeah.
off. That's one thing. Like if it's just dripping out and not going in, that's going to be a problem right there.
If
And
I may, and I don't mean to be redundant, when you're taking the alloy and push it in, that's one of the things I talked about when I taught those third-year apprentices. They weren't literally pushing it in. They were being a little be more aggressive. Push it in. Don't be afraid to push it in. What's going to happen? All that's going to you might wait, you might get a few drips on the floor. So what? You got a
yeah,
good joint.
yeah,
Yep.
just being light on it and just touching it really soft. I've done those before. It's not sucking. You got to push it right into the joint.
Yep.
Okay, excellent. I love that. And pressure tests. I know we didn't dive into a pressure test too much, but you got to pressure test every one of your joints, right? And it's got a whole pressure test. This is our test. That's we know that it's not a leak. Another thing that we kind of just skipped over kind of quickly is when and you went through it, but is having actual oxygen monitor. Nobody does. I don't know anybody that does an oxygen monitor at the end to see if there's no oxygen left in the air going through that pipe. So that was
Yeah.
another thing that you showed me there that I was like, I've never done that. And I changed, I welded and brazed a lot of joints in my day and always flowed nitrogen. Well, after probably the second year, I started flowing nitrogen because it was spec, but I never used an oxygen monitor.
Yeah, it's a little device. It's like the size of a hockey puck. And you push the button after you hook it up with like a quarter-inch tube, plastic tube, because it's low pressure. You're only talking like 5 psi. And when it reads 0, you're good to go. And frankly, we've seen some, highbrow contractors, doing it with finger tests and not really.
They're still doing that. Don't get me. They're still doing that. So if you're gonna do it that way, let it run for a few minutes or 5 minutes.
Yeah,
If you don't know, you got to let it run for a time. And now if you're on a small system, it might be quicker. It might be 2 minutes. If you're on a large system, it could be 10 minutes.
right.
Because I
Absolutely right.
remember hooking up like we were doing 14, like a run of 14 pipes, and we'd have a header built and we'd be using a flow monitor and the flow gauge would be flowing it. But we were just doing it by our fingers, Mike, because we didn't know that like you actually have to get an oxygen monitor out. And most people aren't doing it that way. But if you want to do it right and do it, that's going to save you time. That's the way to do it, man. I love it.
And if you want to have a proof source for
I
your
love
client.
that. I love that. That's a huge one. Now you take a picture of that, a video. Look, on my right now, I'm going to Braze. Got a picture. There's no oxygen coming out, so you don't have to go and cut these joints open to take a look because there are regulators around Canada and North America that will go in and they will say cut out these 5 joints or the end user themselves to make sure the contractor's doing it right, and then that's kind of proof right there.
It's good salesmanship on the part of the mechanic.
Oh, huge, huge. Oh man, we got a few more questions in here if you don't mind.
No, I don't mind at all.
Manufacturers will publish with A2L now long purging based on the line set. Well, it doesn't matter in the if you're using an oxygen gauge, so it's basically time, like depending on the line set, how long would you purge for it? That has nothing to do with it. If you're using an oxygen sensor, you just put it there. It
Yeah.
could be a short, it could be a long amount of time. That's huge.
Takes the guesswork out of it.
David says, I was really interested to see the demo of the soldering starting from the base and moving around the pipe towards the top. I'm correct in thinking that this principle applies with brazing technique too.
Yes.
Yeah,
Same exact technique, David. Same thing.
I love that. Andrew, my good friend Andrew Freeberg, what's up, brother? Ambassador Refrigeration Mentor Community is still showing up. Doesn't have to be here, he knows the stuff, but he's here today. I love it. I really like the statement practice. When I was teaching it, I would cut them open to show them how much penetration actually happens. It's important that you practice and test to make sure that you're doing it correctly. Also, not to overheat the pipe. I only caught a little bit of awesome, Andrew. Paul says the best results on purging, one would use flow regulator and not a pressure regulator. Well, most technicians aren't going to have a flow regulator. I didn't, I had it on the job site, but when you're out there doing a single condensing unit, I think going with that little oxygen thing would be the best spot, because it's when you're using a nitrogen regulator, it's what is it, 0.2 to or 2 to 5 cubic feet you want to get going through there. So it's about 2 psi maybe.
Yeah.
Because you're not going to have a flow. But there are devices out there that you can buy. And Paul, you're right about this. You can buy that will do brazing as well as purging. And so it's already preset in that thing. I think I did one with Western Industries. I think that's who it was that I did some videos with them at AHR one time. And I got it on one of my social medias or one of my courses, so you can check that out. Jay says 1 to 2 psi. I love that. And Tom says 3 to 5 SCFH. Yeah, that's right. Bang on. What else do we have? I think that is what kind of PSI should you run? Oh, that's what Blair says. What kind of PSI should you run? Yeah, 1 to 2 PSI or 3 to 5 SCFH. Mike, it's been amazing. I want to thank you for taking the time to do this. Any final thoughts for any technicians out there that's going to start brazing? Any guys, any advice that you would give them?
The only thing I would say, and I'm speaking for myself, okay? I've been in this industry a long time, and I assumed a lot of things about soldering and brazing, and it wasn't until I got to the ripe old age I am, and I was introduced to this team of experts, and I really learned the right things, and how, quite frankly, I had been doing things wrong, and I had great mentors, and I paid attention. So I think these little tips, like I promised everybody in the beginning, Trevor, everybody's going to walk away with something here. Everybody's going to walk away with a little something. And having been relatively new to brazing when I came aboard CDA, I think I'm pretty good at it now, and it's because I pay attention to the techniques.
Yeah, I love that. It's huge. It's all about technique, right? And you do the proper technique. Now, this is going to save you time. Why do we do that? Why does a refrigeration mentor bring the top people from around the world to come on this? So you can go out and practice this, and you can use this out in the field. This is going to save you time. Oh, well, I got to set up an oxygen monitor. Oh, I got to get a flow regulator. Oh, I got to do this. That's just excuses. Just get it. And then you watch over time. The first time might take a long time. The second time might take a long time. But that third, fourth, fifth time, you're just crushing it. And that's what it's all about. Learning, growing, and sharing this. Please share this with other people. There's so many people that need this webinar. They need to watch this. Go to the YouTube channel and watch this. Mike, I want to thank you so much for taking the time to do this. We'll do something like this again. Appreciate your time and your experience, my friend.
It's been a privilege. To all you folks out there, be safe.
Okay.
Thank you, Trevor.
Love it. As well, everyone, have a good one. And as always, let's get a conversation going. See you, everyone.
Bye now.